So I'm going to tell you about a collaboration with the lab of Daubechies in evolutionary anthropology here at Duke. And they study teeth and bones with homologous features, meaning with features that are similar in function. And they want to compare them quantitatively, study them statistically, and because they want typically to test different hypotheses of evolution. Next slide, please. So the standard way of doing that is when you have, for instance, here a collection of teeth that you want to compare, is that people would mark. They used to do it by hand and they now do it on computer, but they would mark homologous features and they would then take those points with their coordinates as a proxy for those surfaces and compute distances by moving one of the 10 points on one surface as close to the 10 points on the other surface as possible and look at all the sum of the square distances. That's the Procrustes distance. Next slide, please. Now, they want to do this in a way that does as well for biological purposes as the Procrustes distance, but automatically, without having to mark lots of bones and teeth. There are many reasons for that, but one of them is that if you have to mark them by hand, you will just do enough that you can do a study that is statistically significant, and you're not using the 99% other samples that you have in your museums and collections, which would, if you could use them all, which would give you much more definitive results. So that's one reason. There are many others. Next slide, please. So we can, of course, do a similar thing, computational. We can put a lot of points on one surface, a lot of points on the other surface, and then find the correspondence of those lots of points more or less equally distributed. That does the similar thing as well. And we call that the continuous Procrustes distance. And we were very proud of it at the start 10 years ago because it was very good. And so we call it the CP distance, continuous Procrustes. And here you see two teeth and you see a texture on one tooth transported to the other tooth by means of the mapping that we found through such optimization. Yes, next slide, please. And here is an example of a placement of 5 groups of each of related species that are clearly where we have 10 exemplars. They're reasonably nicely separated by means of this automatic method, at least as well as they were done by the manual method. Next slide, please. But in fact, we can do much, much, much better, because what you saw in that graph of all these points was that some things were close to each other and some things were far from each other. And we can use a computational approach, something that would have been completely impossible without computation, to get a better insight in that collection, which probably has a lot of structure inside this high-dimensional space in which we embedded it. I mean, hundreds of points, each with 3 coordinates. I mean, we're in the thousands of coordinates for a surface. So what happens is that in that enormous space, there is some very sparse structure that represent teeth of lemurs, and when things are very close to each other on that sparse structure, it's reasonable to approximate it by a little tangent surface. And you can, next slide, please, and we can slowly march through the next 3 slides. You can, within each of those, look at what are called random walks, for which we have beautiful ways of computing them and of understanding them physically. And then by jumping from one to the other, you can make a longer random walk. Now you're no longer on the data set. Next slide, please. It's a little bit like these little slivers that are all a sequence on animals. I mean, each one of them is nice and flat, but and they overlap, but together they give you an impression of the whole surface. And that's a similar thing to what's happening in these diffusion methods. Next slide, please. And so by building these random walks, we understand how diffusion works in the data set, and that tells us a lot about the geometry. And then we can understand a better way of building distances. And that's what I show here on the right, with exactly the same data set. From the continuous Procrustes distance, we get to these diffusion distances, to the point they're so much better that we have started to call the continuous Procrustes the crappy distances, because, well, we were proud of them 10 years ago, and we do so much better now. Next slide, please. But in fact, you have much more, because each tooth we viewed as a tooth, as one point in this high dimensional space. But it's more than a tooth, than a point. It's itself a surface. And mathematicians call this, when you have a whole smooth collection, but where each one of them has extra structure, they call that a fiber bundle. And you can then build diffusion on that whole collection and start to study that. And this is something that my student Ingrid Daubechies did when in his PhD. And for instance, you can then use those, next slide, please, to understand how each of them can be mapped to a template surface. And that makes it possible for us to now register things much better. Because of course, the red points that I sampled on the tooth up on the upper left and the blue points on the tooth on the upper right were not going to be exactly in corresponding points. I just took them at random. But now, because I can all refer to this common template, I can see which average of 3 blue points, 1 red point is, and I can map it to that exact corresponding point on. So we have much better correspondence maps, which we build as a result of this whole computational effort. Next slide, please. We have used this in order to build, to carve up teeth into homologous regions rather than try to find homologous points. And this has already been used, this kind of decomposition, by students in evolutionary anthropology as part of the data that they can then use for their work on testing evolutionary hypotheses. Next slide, please. You can also, by looking at the points that correspond to each of the teeth on the eigenvectors of these big diffusion operators, next slide, you can understand the geometry of all these. Next slide, please. And next. And that then gives you a better way of understanding the geometry of the data set. In a way, what you have is many, many different summaries of the geometry of the underlying collection from all these correspondences. And that has led us to, next slide, to this plot on the left. So we started from the diffusion distance, we started from the crappy distances, which we were so proud of. We made the diffusion distances, which are very much better. And using the maps and that interpretation that Ingrid Daubechies built, we get this much better separation, where incidentally, the species that are closely grouped together happen to have the same food preferences. Next slide. So now we can go quickly through the next few slides until the end of my presentation. What you see here are snapshots from a tutorial that was developed by one of the computational mathematicians to teach the biologists software that we had developed that will help them in their study, so that they don't constantly have to come and ask us to do things for them, which they're reluctant to do. Plus, we want to give them the tools to do it themselves. That's where I'll stop. Thank you.